If the universe's life was one long story, its main character would be the Hubble parameter, or the Hubble rate. The Hubble rate tells us how fast the universe is expanding throughout time. And knowing this rate helps us find out how old the universe is, what the shape of the universe is, and what the future of the universe will look like. So you can imagine scientists are working really hard to figure out what this expansion rate is today. The thing is that when physicists try to measure this expansion rate in different ways, they seem to get different answers, and it's getting pretty contentious at this point. So on today's episode, is this apparent disagreement in the Hubble measurement real? Does it come from new physics, or just some less dramatic reason, like measurement errors? And when will we know for sure whose measurement is right? All that, plus a very special guest after the break.
This episode of Why This Universe is supported by Wondrium. Wondrium is a mind-blowing subscription service that offers thousands of video and audio courses on a huge range of topics. I've been a fan and regular consumer of Wondrium's content for the last 15 years or so. Over that time, I've listened to dozens of their courses, including ones on history, philosophy, literature, math, and science. For me, it's like taking an intro-level university course from a great professor on a subject you've always wanted to know more about, but without the big tuition fee and all in the comfort of your own home or daily commute. A few years ago, I wrote and presented a series of lectures for Wondrium called What Einstein Got Wrong. Over those 12 lectures, I described some of Einstein's biggest blunders and mistakes. These included misconceptions that he had about things like black holes and gravitational waves, as well as his failed attempts to find a grand unified theory. So if you want to get a more complete picture and maybe a more human picture of Albert Einstein, or to learn about just about anything else, check out Wondrium and give them a try. Sign up now through our special URL to get a free month of unlimited access. Just go to wondrium.com/universe. That is wondrium.com/universe.
You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago.
Before we dive into the divisive measurement itself, let's go back and tell the story of why this number, the Hubble rate, is so important. The story starts with general relativity, our best understanding of the force of gravity. This theory revealed that space in its entirety must be either expanding or contracting, depending on the matter and energy content of the universe. This result came straight out of Einstein's field equations. This realization set the stage for the science of cosmology, because you can imagine that whether our universe is expanding or contracting has lots of implications for its past and future. In the late 1920s, astronomers, for the first time, measured that our universe is actually expanding, and since then, astronomers have been making heroic efforts to improve these measurements. In 1970, the cosmologist Alan Sandage wrote a highly influential essay in which he argued that for decades to come, the science of observational cosmology would be essentially a mission to measure two numbers: how fast the universe is currently expanding, and how fast this rate of expansion is either slowing down or speeding up. And while boiling down all of cosmology to just these two numbers is something of an exaggeration, it is true that these two numbers in themselves have taught us an enormous amount about the energy and matter in our universe and about how our universe has evolved over time.
Today, in this episode of Why This Universe, we're going to talk about one of these two important parameters, the current expansion rate of our universe. We also call this number the Hubble constant. And we have with us today the cosmologist Wendy Freedman, who is one of the most important figures in the history of making these measurements. Among other roles, she was one of the leaders of the Hubble Space Telescope's Key project, which in 2001 produced what was by far the best measurement at the time of the Hubble constant. She spent a lot of her career at the Carnegie Observatories in Pasadena. Starting in 1984, she became the first woman to be a permanent member of their staff in 1987. She became the director of Carnegie in 2003. But then in 2014, we're lucky enough for her to leave Carnegie and come to the University of Chicago, where I've gotten to know her. Welcome, Wendy. We're excited to have you on Why This Universe.
Well, thanks, Dan. I'm excited to have this conversation with you.
Let's start, because I imagine a lot of our audience won't really know what we mean when cosmologists talk about the universe expanding. So what's your kind of go-to analogy or, way of explaining what it means for the universe to be expanding? I bet you have some good ones.
It's a hard concept to get your head around, that the universe is expanding. And I think our tendency initially is to think of something like a bomb that's exploding and it's exploding into something. And that is not the way that the universe is actually evolving.
In other words, the things in space aren't actually all moving away from each other the way debris would in an explosion. It's just that the space between all these things is getting bigger.
And what we learned from Einstein and Hubble is that we live in a dynamic universe. It's expanding, it's not static.
So the theory of general relativity revealed that space is not static, and that it instead must be expanding or contracting. But in the early days of cosmology, there was a lot of hesitation to accept such a strange new picture of reality. Despite this being Einstein's own discovery, this was a famously hard pill for him to swallow.
He talked to the astronomers of his day, and we didn't even know about the existence of galaxies at that point. And we looked at the stars in the Milky Way, they weren't moving. So there was no evidence for an expansion of the universe. And so Einstein, even though he recognized the universe either had to be expanding or contracting, the way that Einstein solved that was to add in something to force the universe to be static. Turned out that wasn't stable.
So, Wendy, everyone talks about Einstein having this strong objection to the universe expanding, and he went to great lengths to find solutions to his equations where the universe would be static. As far as you're concerned, as far as your reading of history goes, was this just an empirical objection? Like you said, he talked to the astronomers of the day, and they said, well, we don't seem to notice the universe expanding. So he insisted on that? Or did he have some sort of other, like maybe philosophical objection? I've never really been able to put my finger on what what his thoughts on this question were at the time.
Yeah, it's an interesting question. I mean, Einstein really did think ahead in terms of, many things that weren't being considered at the time. I mean, nobody was thinking about space that was curved, or the interaction of matter and space, or energy and time. I mean, he was willing to consider things that were very different than that were the prevailing ideas at the time. But certainly philosophically, the idea that the universe was expanding when we didn't even really understand what the nature of the universe was at that point, I don't think it was not something that he jumped to, even though he was willing to make leaps in so many other directions when people weren't thinking in that direction.
Mm-hmm.
Despite how clearly his theory was pointing to an expanding or contracting universe, it would take some remarkable evidence to convince Einstein that it was really the case. And that evidence would come in 1929 thanks to Edwin Hubble. Hubble and others discovered that galaxies far away are moving away from us. And the farther away a galaxy is, the faster it is moving.
The implication of Hubble's discovery was that if we look back in the past, then galaxies would have been closer together. And if you extrapolate them farther back in time, that would have implied a time in the universe when matter would have been very densely packed. And it would imply that the universe had a Big Bang beginning.
So studying today's expansion of the universe doesn't just tell us about today. It tells us about the universe's origin and where it's headed.
So another thing I wonder about from this time is it seems like a remarkable coincidence that in the late 19 teens, Einstein puts together all the theoretical work to show that the universe needs to be expanding. And then just a little over a decade later, we measure it. Why were those things why do those things happen at a similar time at all? Why weren't they separated by, if not decades, hundreds or thousands of years? Is it just a total coincidence that these two things kind of unraveled on the theory and observational side, in such close proximity to each other?
It's a really interesting question, and I think also we haven't talked about what made it possible for Hubble to make his discovery, and that was that Henrietta Leavitt, an astronomer who'd been working at the Harvard College Observatory in the early 1900s, had been studying these stars that we know of as Cepheid variables. And she discovered a relationship between the brightness of these stars and how fast they were changing in their luminosity. And that became the basis, using the inverse square law of light, for how astronomers could measure the distances to galaxies. So if that hadn't happened, so many parts of this that really came together in a very short space of time. And everything we've done on the distance scale since then depends on her initial discovery. And she's not well known. It was an exceedingly important discovery. And what Hubble did, and what we did with the Key Project, and what people are still doing today, is based on the work that she did. So
yeah, I feel like Leavitt is starting to get her due now, but for a long time she was considered a minor figure in astronomy, very, very unjustly. So Wendy, we've been talking about this measurement that Hubble and Leavitt and all these people collaborated to make. What was the measurement? What was the final number that appeared in these papers?
So when Hubble published his paper in 1929 that showed this relationship between velocity and distance, the slope of that correlation, which is a measure of the expansion rate of the universe, the slope he got was about 500 in units of kilometers per second, and then a distance unit of megaparsecs, millions of parsecs. And that is much higher than the number that we measure today. It's about a factor of 7 or so smaller what we measure today. But it was, at the time, the best that he could do with the photographic plates that he had. And he was unable to correct for the presence of what we now know is intervening dust between us and the Cepheids. So it was clearly a discovery, but the actual expansion rate we've refined quite considerably since that time.
Yeah, so in other words, he was able to correctly identify this relationship between the distance and the velocity, but precisely what that relationship was still very highly uncertain in Hubble's day. Okay, so in the 1920s and the era after that, the main way that astronomers measured these great distances and connected them with the expansion rate of the universe was using these Cepheid variables that you talked about. In the decades since, or even in recent decades, like what are the techniques that modern astronomers, such as yourself, rely on to make 21st century versions of these kinds of measurements?
Yeah, well, interestingly, Cepheids really have remained enormously important for measuring the distances to galaxies, and they're what we use for this Hubble Key Project that we did when the Hubble Space Telescope was first flown. And Hubble used other techniques in addition to the Cepheids to try and move out farther. And we want to do that because Cepheids themselves aren't bright enough to get into the realm where you're actually participating in the overall expansion without having the effects of the interaction of galaxies, which are interacting via gravity. And so what we most often use today are objects called supernovae, bright supernovae, a particular kind of supernova, which has the exciting name Type 1a supernova.
Astronomers are great with their naming conventions.
Great names. They're very bright, and we can see them over vast distances and much greater than the distances we can measure directly using the Cepheids. At the time of when we started the Key Project, we still didn't know the value of the Hubble constant or the expansion rate to better than a factor of 2. And so in the 1970s, 1980s, those were the kinds of arguments that astronomers were having within the field. And it was, again, very difficult to pin down a very accurate and precise measurement of the Hubble constant.
Yeah, I remember when I was in college, I took my first cosmology class, and when this number, the Hubble rate, came up, the expansion rate of the universe, they said, well, it's somewhere like between 50 and 100. That's the best that anyone could say at the time. And what's the uncertainty we have today on this quantity?
So at the current time, I would say we have we know it to better than 5%. I would say that
5%.
we know that with if we want to say without any quibbling about it at all, we know it to 5%.
But here's where the big contentious tension arises. Different groups of physicists have measured the Hubble rate today even more precisely than that 5% uncertainty. And what they find is a statistically significant disagreement depending on how they take their measurement. So there are two big ways physicists make this sort of measurement.
So on the one hand, cosmologists can go out and look at things like Cepheids and supernovae and things and actually directly measure how fast our universe is expanding right now. But you can also look at things from the early universe, like the cosmic microwave background, and deduce from that how fast our universe has been expanding and what the current rate of expansion should be like today. So in practice, you should get the same number when you do it these two different ways. But in reality, those local measurements are getting numbers like 73 kilometers per second per megaparsec. And the early universe determinations give something smaller, like 67 kilometers per second per megaparsec. They're not very different, but they're statistically significant in how different they are. And maybe this is pointing toward there being some exotic new physics or new forms of energy that were present or playing out in our universe during its first few 100,000 years. So Wendy, what can we do to improve this situation? How are we going to find out if this tension is really an indication of new physics or not? What has to happen for us to learn that?
We're really anxiously awaiting results from a satellite called Gaia. It's a European satellite that is measuring direct parallaxes to Cepheids in our Milky Way galaxy, and also other kinds of stars like red giants, which is what my group's been working on for the last few years, to try and measure the Hubble constant independently of the Cepheid calibration. But at the moment, there are uncertainties in those measurements that are, might actually reach a 5% uncertainty. And so we're in this period where there are potential uncertainties that could be affecting these results. If you don't take those uncertainties into account, you say, well, there's this, really enormous discrepancy. And it's like any time when you're at the forefront of a field, you don't know what data are going to be left standing by the end, once the fog clears and you have a really clear signal that the systematic effects that you need to worry about have been taken into account and are at a level that are small enough to claim a significant discrepancy. So that's where we are now, which is kind of an exciting time because there's this potential that we could learn about new physics in the early universe, but at the same time, we want to make sure that we're not just learning something astrophysical about the Cepheids themselves or still some uncertainty in the calibration.
One possibility is the way we measure the Hubble constant has some biases or some problems in it, and it shifts the answer a few percent in one direction. Another possibility is that the way we extract the Hubble constant from the cosmic microwave background observations are biased in some way, and it pulls it in the opposite direction. And in either case, we're bringing them into concordance with each other. But a third possibility is that, something about the laws of physics is different than we currently think that might explain why these two different ways of getting at the same number give us different answers. Like what kind of so there, like I said, a lot of ink has been spilled over these sorts of speculations. But in your mind, what are the possibilities in this latter category that you're most excited about?
A lot of ideas have been put forth, and a lot of ideas now no longer are consistent with a large body of observational and experimental data, which is what makes this an interesting problem. I think a lot of excitement early on when this discrepancy first surfaced was maybe there's an additional neutrino, some kind of sterile neutrino that would allow the expansion rate to be higher early in the universe, and that could cause this discrepancy between the nearby and the more distant measurements. And that doesn't now seem to be consistent with really precise measurements of the fluctuations in the power spectrum of the microwave background. And a number of other things that have been looked into, and another possibility, especially early on, people were excited about the idea we now know that there's a dark energy component in the universe, and that's causing the universe to accelerate in its expansion. So maybe we don't know what the dark energy is at this point. That remains a mystery. So maybe that could allow for some difference between what we're measuring.
If you had to look at all these different options, and I'm a odds maker at Vegas now, and I'm your best friend, and I say, Wendy, we want to take bets on what's going to resolve the Hubble tension. Give us your best possible numerical estimate for the probabilities that it's a problem with the Cepheids, it's a problem with the cosmic micro-vacuum determination, or it's some sort of new kind of physics, something exotic that we don't know about. How do you best guess at those odds?
So if I'm going to leave it open, I would say 50-50, because I don't know where it's going to resolve. I don't know where it's going to resolve. I think, I think there are intriguing possibilities. I think the most exciting, of course, would be that there is some new physics, right? I'd love it to be that way.
The easier question is what we want to be true. What we want to be true is new physics. That would be great. How long is it going to take for us to put the final nail in the coffin of this question and answer it once and for all?
Well, I think what I was just about to say, what I'm really excited about now, so the James Webb Space Telescope, we put in a proposal for James Webb time, and we have time to do Cepheids and the tip of the red giant branch in the same galaxies, and another technique that we've been developing using a kind of a star called a carbon star. It's a larger telescope. It has more light gathering power, so we can get very high signal to noise. It's sensitive at infrared wavelengths, and so these questions of dust and metallicity, those systematic effects will be less.
So for the non-astronomers in our audience, telescope time is kind of the currency we deal with among astronomers. You take these big public telescopes that many scientists get to use, and you apply to get everywhere from seconds to hours to days or whatever on these instruments. I'm, for one, glad to see that James Webb's time is going, at least in part, to this important question of the Hubble constant.
Yeah, I think it'll be fun. And I think, all these issues of do the better measurements using both techniques agree or not. And the other is Gaia, the parallax satellite. They will have further releases of data over a longer time baseline, and their systematics will come down. Right. And then even further along the horizon, there will be, for example, the Giant Magellan Telescope, which is a optical 25-meter telescope that will be based in Chile, which University of Chicago is a partner in. And is
a truly gargantuan telescope, right?
Yeah, which will give us very high resolution, and again, allow us to measure galaxies that are either more distant that we can measure now accurately, but also getting at these questions of, is there crowding of images that might be affecting the luminosities that we're measuring for the Cepheids? So there are a lot of things, I think, in the next few years that will help this problem enormously, and we do need to understand it.
I can't wait to see how it all plays out.
Me either.
Thank you so much for listening to Why This Universe. If you want to support us more and get access to some exclusive content like exclusive interview clips, Ask Me Anything episodes, the opportunity to ask us questions, and a free sticker, you should definitely join us on Patreon. You can find us at patreon.com/whythisuniverse, and we really appreciate all the support that we get through there. Today's episode was produced and edited by me, Shalma Wegsman. My co-host is Dan Hooper, a professor of astrophysics at the University of Chicago and Fermilab. He's also the author of many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. And Why This Universe is brought to you by the University of Chicago Podcast Network.